So this week we will be covering radicals. And before we do that, we need to review some of the properties we've already learned of exponents. So the first thing I want you to remember is this property here, where the definition we've learned of exponents is in terms of serial multiplication. So if I have x times x times x, so on and so forth, where n is the number of x's that I have, then I can rewrite this as x to the n power, right? Now, the next thing I want you to remember is this over here, which is the commutative property of multiplication, where I can have a times b times c, can be rewritten as c times b times a, or b times a times c, etc., etc. I can rearrange these variables, and it doesn't matter which one I multiply first. It's all going to come out the same. Now, down here, I have kind of a combination of those two rules that's going to allow me to rewrite this. So in this orange color, I have a term x times x, and in this pterodactyl pink, I've got x times x times x. Now, because it doesn't matter the order in which I multiply these, I can write these all out. X times x times x times x times x. We've got 5 here, 2 of them coming from this pink term, 1 of them coming from this second term here. I can rewrite this as x to the 5th, right? Now I can also, instead of writing this out in terms of all these x's here, I can simplify this orange term as x squared, and I can simplify this pink term as x cubed, and then I can rewrite this as x squared plus 3, right? And the 2 is coming from this term here, and the 3 is coming from this term here, and I get x to the 5th, which is the same as what I got here, right? I can then generalize this. Instead of using specific numbers, I can just have x to the a times x to the b, and define that as x to the a plus b. Now, this is what we've learned of exponents, and we notice that they only work for integer values of x. Actually, no, this is wrong, what this should say. Let me fix this. This is supposed to be the exponent here, not the base, right? So if I say this n here is like this n here, right? I can have x squared, I can have x cubed, I can have x to the 10th. Those are all things we can understand, but what we cannot understand yet is something like this here, where I have x to the 0.2, right? I can't write that as x times itself 0.2 times. That doesn't make sense. I could also give you a more concrete example. I could say, what is 9 to the 0.5, right? I will tell you that this has some numerical value. There is a solution to this. There is an answer to this. As we currently understand it, this does not make any sense. So the first thing that we want to think about is, what about x to the n, where n is not an element of the integers? Something like x to the 0.5 or x to the 0.1, anything non-integer value. What meaning could that have? And how can we extend our definition of exponents to encompass that meaning? So we will see down here, right? I've got the option where we could just say, well, if exponents are defined as serial multiplication, and I can't have serial multiplication for anything other than integer values of n, then this could make no sense, right? I could simply say that If this definition is the definition, it's the most general definition, then something like this here makes no mathematical sense whatsoever. Alternatively, we could try to come up with a more general definition of exponents that would allow us to keep everything we've already learned about them, maintain all those properties, and extend that definition to non-integer exponents, and come up with a more general definition that has broader meaning and is more applicable. Okay? So that is the first thing I want you to think about. The next thing I want you to think about is, given the property we've already established where x to the a times x to the b equals x to the ab, or excuse me, x to the a plus b, let's think about if we have x to the 1/2. Right? So far, we do not know what this means, or if it even has any meaning at all. With our current level 1 enlightenment of exponents, this has no meaning. However, if I apply this rule here, which we've already established, then x to the 1/2 times x to the 1/2 must equal x to the 1/2 plus x to the 1/2, or excuse me, x to the 1/2 plus 1/2, not x to the 1/2. That simplifies to x to the 2/2, which of course simplifies to x to the 1, which we can just write as x. Okay? So x to the 1/2 times x to the 1/2 equals x. All right? Now, I'm going to rewrite this term here as x to the 1/2 squared. Now I have x to the 1/2 times x to the 1/2. I see that that is just x to the 1/2 squared. Right? Now, I'm going to say that that equals x. We already solved that over here. Okay? Now, what happens if I rearrange this by taking the square root of this side, taking the square root of this side? If I take the square root of something that I'm squaring, that's just going to be whatever is inside of here, right? Because I have x to the 1/2 squared, square rooted. So this will become x to the 1/2. And this will remain as the square root of x. So now we have shown that x to the 1/2, right? We didn't know what that was when we started. I just put it there. We showed that x to the 1/2 has to equal the square root of x. Okay? So that is a pretty substantial breakthrough. I will mark it here. Like that. This little tidbit is going to be the basis for all our future understanding of non-integer exponents, right? This exact logic here that relates a non-integer exponent to a radical. So, returning to the question we had on the previous screen, if I have 9 to the 0.5, I can rewrite that as 9 to the 1/2. And if x to the 1/2 equals the square root of x, then 9 to the 1/2 should equal the square root of 9, which equals 3. Okay? So I can rewrite this as 9 to the 0.5 equals 3. So we've taken something that a few moments ago had no meaning to us whatsoever. We've applied the principles of math that we've already learned. We've shown that logically, with the rules of exponents we've developed, this has to be true here, which then allows us to see that this has a numerical value of 3. So that is a major breakthrough in our understanding of exponents, that we have solved our very first non-integer exponent problem here. Okay, so I will leave you there with the first video, and I'll continue on in the second video, and we are going to try to come up with something more general than this. Instead, we're going to try to come up with x to the 1 over n equals what? Right? We've just done it for 1/2. We want a property that will allow us to understand any non-integer exponent. And more generally, we could even just rephrase it as x to the n, where n is not an integer. Okay, so make sure you understand everything in this video, particularly the things we covered in the first screen here, right? If these are shaky or don't make sense to you, then nothing else going forward will. So make sure you understand all of this. Make sure you understand the argument we've gone through here, and how we got to this, and how we generalized that to solve our first problem here. And think about how, going forward, we will be able to come up with identities for this and for any general non-integer value of n.